Hello and welcome to calculus class. Today, we are going to be learning about derivatives and what they do, what they are, how to do one, what is a derivative. Let's just get right into it. So, what is a derivative? So, a derivative in relation to a function is the rate of change. It's an expression that represents the rate of change of a function. So it's a line on the graph that will show the slope or the rate of change of the graph. One way that we can find it is by using the difference quotient formula right here. So that would be f prime of x equals f of x plus h minus f of x over h. And so h would be the difference, the delta x, or the change in x between 2 points on the graph. The smaller h is, the more exact our line is. And so this formula with ideally a very small value for h would get a line on the graph that is very close to the derivative or the difference quotient of the function. And from there, we can use that line to kind of get an educated guess of what the line looks like and then find the true derivative from there. Another way that we can kind of find the derivative of the function is by using local linearity. Now, this is a concept that's a little bit tough to grasp for me, but basically, I think about it as the big zoom, right? I have illustrated here, each time you zoom in, you get a little bit closer and the line looks a little bit straighter each time until you get zoomed in really close. The difference between the points is so infinitesimal that the line looks like a straight line. And so you're basically getting a linear slope, just like in a linear function like we did in Div 1. You're getting a linear slope where the distance between it is so small, it looks like a line and it'll have an instantaneous slope, right? So it'll have one slope pretty much between point A and point B. And so that would give us our instantaneous slope or our derivative. The other way to do this, although, is with a tangent line. So at the end of the day, our local linearity is going to give us a secant line. So the secant line is a line with two points on a graph. The line that cuts through both those points is going to be the secant line. As you can see, this is kind of like a line of best fit, right? It's going to give you an approximate bit of the slope. Like if the function was linear, this is what the slope would be, right? But the tangent line is a line that crosses through one point on the graph, and it runs alongside the graph as a linear function, right? And this is going to give you the slope at that one point that it touches on the graph. This is going to be the difference quotient or the derivative of this one exact point, right? So it's not going to be like this little bit in the middle, like, oh, where is it? Where's the difference quotient? Where is it actually modeling the slope? No. This exact point, this line will have the slope of that point, which brings us to how do we find that line? Well, I have an example here for you. So that difference quotient is going to be a little different. It's different line. Let's say I have this function, right? My function is f of x equals 2x cubed plus 7, right? It's a hard equation. How am I going to know what the slope is at a given point? Well, I plug it into this handy dandy little graph using limits. Now, we haven't really been over limits that much, and it is a little bit of a tough concept to grasp, but basically, limits, put simply, is in the, let me go back a little bit to our derivative equation. So, right, our derivative equation here, ideally, we want delta x, the change in x, or h, to be so close to 0 that it's basically 0, so the line will basically be our derivative line. But it can't actually be 0 because you look, h is on the bottom of the function. You can't divide by 0. That's where limits come in. Limits allow us to divide by 0, adding in this operation of limit of h approaching 0. And so at a certain point, we'll be able to divide by a number that is approaching 0 and it has a asymptote of 0 and is very, 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 very close to 0, but is never quite 0, but allows us to get the accurate function. So back to our equation here. I've set up our function of 2x cubed plus 7 into our derivative difference quotient form with a limit, right? In limit form of limit of h approaching 0. So this operation just means at the end of the function, we can divide by 0. So we can plug in 0 for h at the end when we're done here. So first we need to FOIL out some things. So I've foiled out our parentheses here with, because our parentheses x plus h and our parentheses x are being cubed. So everything here has been foiled out, simplified a little bit, brought together, and then now divided by h. Notice the limit travels with us. This was a little bit hard for me to grasp, but the limit is actually an operation that's attached to the equation. It's not just part of the function of function prime of x. The limit's not attached to that. It's attached to the function. So it's an operation kind of like the equal sign or like the division, right? It's attached to the function. It's something you're going to be doing with the function. So it travels with it as we simplify through. We're not actually doing any plugging and chugging or anything here. We're just simplifying the equation down to right here. So 6x squared plus 6xh plus 2h squared. So now what we have here is our our function here. And now it's hard to do anything with this because excuse me. Sorry, I got a little lost there. What we do here is we use the limit. So, right, like h is approaching 0, we can use 0 for h. So we can plug in 0 on both of these functions here. These each have h attached to them. So if h equals 0, it will be canceled out. So these ones will each equal 0. These ones will each equal 0, leaving us with a derivative of 6x squared. And that is our difference quotient for this function. This is going to be our rate of change for this function at any given point. Will be whatever the x value is, 6x squared. And that's basically how you use limits to find the derivative of a function. If you have any questions, you can email me at cyrus.brown@theparker.org. I will be happy to field any questions you have. For homework, I'm going to need you to complete 20 practice problems using these limits and derivatives. It's probably going to take a couple of hours, but it is valuable practice and will drill it into your brain well enough that you can give a 7-minute talk about it for your assessment. That is it. Have a wonderful night, and I will see you next time in calculus class.